Okay, hi everyone. Welcome to GOCC. Today we're happy to have Sylvester Zhang from University of Minnesota speaking. Yeah, take it away, Sylvester.
All right. Thank you for the invitation, and thank you all for coming here. So I'm going to be talking about the Greene-Kleitman correspondence and its connection to Viennot's shadow line construction for the Robinson-Schensted correspondence. I guess so. The central object here is not in the title, which is the Robinson-Schensted bijection. So in short, it's a bijection from the symmetric group, which are all the permutations of n, to pairs of standard Young tableau of the same shape. So standard Young tableau is a filling of a partition, and a partition is just an array alignment of boxes such that the number of boxes in each row is weakly decreasing. And then, so a standard Young tableau, or I will sometimes write SYT, is basically you want to fill out the boxes with numbers 1 to n, such that every row and every column is increasing. So here's an example. So you can see that if you read every row or every column, the numbers you get are increasing. And so the original definition of the RS is via some sort of algorithm. And so I just want to give like a quick example of what it is. And very soon we'll switch to an alternative definition, which are in some sense better than the original algorithmic definition. So let's say you start with a permutation 2, 3, 4, 1, 5. And then and you're going to read off the numbers from left to right and then iteratively build up your tableau. So first of all, you take the number 2, and then you want to build off a tableau out of the empty, the ambient partition. And so you get a tableau with only one box, and the shape is, and the filling is 2. And then you take the next number 3, and then you will try to add the number 3 to the first row. And then if you can do that, then you succeeded, and then you get the next tableau. And then you're going to try to add the next number, which is 4, to the first row. Again, now you get a next tableau. So nothing bad is happening. But the next thing you will do is that you're going to add 1 to the first row. But you're not able to do that because if you put 1 over here, then it's not increasing anymore. And so if the number you're trying to add is not greater than the largest number of the row, then you're going to replace it with the smallest number here, and then take that number out and then insert it to the next row. So what you're going to get is 1 is going to bump the 2 out, and then you will insert 2 to the next row. So you're going to get this. I guess this is somewhat not very interesting example because you only see bumping once, but then the next thing you do is that you will add 5 to the first row. So this gives you the first tableau in the image of the bijection. The second tableau can be obtained in the following way. You record the shapes of the insertion algorithm, and then you just add numbers 1 to 5 to the new boxes in each step. So the first tableau is usually called the P tableau or the insertion tableau. And then the other tableau is called the recording tableau or the Q tableau. And so, so this is the definition. Okay, if you If you're not familiar with this definition, that's okay, because we'll see a different one. And so the DRS algorithm has a lot of applications. It's very important in many areas of combinatorics and representation theory. So just to give some example, it can be used to, it can help to in some sense parameterize or understand the irreducible components of the Springer fiber. So I would say these are the applications or connections. And it can be used to parameterize the symmetric group into what's called Kajan-Luzik cells. So there are certain things in representation theory called Kajan-Luzik polynomials, and then these polynomials gives a way to separate the permutations of the symmetric group into different cells, and then in that context, you can use the RS to describe the cells in a sense that if two permutations are in the same cell, then they have the same insertion tableau. Or if they're in the right cell, then they have the same insertion tableau. If they're in the same right cell, they have the same recording tableau. So it's very useful in that context. And some other application is that there's a generalization called R Robinson-Schensted-Knuth, which is instead of so your input will be instead of permutations, but you have more general words that can have repeat of numbers. And then that generalization is useful in multiplying Schur functions. To get the little Richardson number. So that's just some sort of evidence that this is an important stuff that we wish to understand. And there are many ways. So this is the old object, and there are many ways of doing it. So let me kind of switch gears and then talk about something from a different perspective, which is about Greene-Kleitman theory. So any questions before I move on?
Yes, sorry, could you repeat the definition of Q, please? So the last, what does it exactly do? It always goes row-wise?
Okay, so you get a sequence of tableau when you do the insertion. So you get this sequence. And then so you sort of just copy the shapes, the partitions of each step of your insertion algorithm. And then you add 1 to the first step, you add 2 to the second step, you add 3 to the third step, you add 4 to the fourth step, and so on and so forth. And then you build up the tableau in that way.
The last tableau, okay, in the last tableau, the 4 and 5 are swapped.
Oh, my bad. That's a typo.
Okay. So
that's a typo. Thank you. So 4 is here, and then the new box is here. So this guy should be 5.
Okay, thank you very much.
Yeah.
What do you mean by the index to irreducible components of the Springer fiber? Can you elaborate on that?
So if you have, okay, I'll just briefly explain it. So if you have a nilpotent element and its Jordan type is some kind of partition, and then it is known that and then you know associated to that nilpotent element, you get a Springer fiber, which is a fiber of the Springer resolution, and then its reducible components due to Spellstein is parameterized by standard Young tableaus. And then if you take 2 irreducible components as irreducible subvarieties of the flag variety, you can apply the relative position map of the flag variety on those 2 irreducible components. And then the relative position is going to be a permutation, and that permutation is the inverse of the a Robinson-Schensted algorithm that you applied on the two standard Young tableaus corresponding to the two irreducible components. So that's sort of the
Oh, I see.
story.
Okay.
But
Okay,
it's too
thank you.
complicated to go over the
That
full.
was good. Yeah, that was the amount of detail I wanted.
All right. So now I'm going to talk about Greene-Kleitman theory. So Curtis Greene and Kleitman, they were studying sort of a kind of a unrelated sort of posets theoretic question. So they were interested in the K-Sperner families, which are basically subposets of a poset, a P some poset, which doesn't contain any chain of length more than K. Chains of length greater than K. So basically, you can think of a K-Sperner family to be a union of, at most, K anti-chains. So if you take K anti-chains, I should probably define what are chains and anti-chains. And maybe I should also define what a poset is. So sorry about that. Well, a poset is a partially ordered set. And so you have some elements, and then they are partially ordered. And then you can usually represent the partial order using a Hesse diagram. So I'm drawing the arrows here. If A is pointing towards another element, then in this case, A is bigger than B in the partial order. But these two elements, there's not a connected path from one to other, so they're not comparable to each other. And so a chain is a totally ordered subset. And an anti-chain is a pairwise incomparable subposet. So for example, these three guys form a chain of the poset, these three guys, and then these two guys form an anti-chain of the poset. Okay, so going back to Greene and Kleitman's motivation, so they were studying the structures of these K-Sperner families, which are, a subposet which doesn't have chains of length K. And if you have a subposet which doesn't have chains of length K, usually you can write it as a union of K, at most K anti-chains. And like, if you take K anti-chains and then just like take their union, then obviously you will not be able to find any chains of length more than K. And so they basically proved some structural theorems about these K-Sperner families that, for example, they form a distributive lattice, and then there's a maximum of the lattice or something like that. And then later on, they found that this seemingly unrelated story can be related to the Robinson-Schensted correspondence. In some sense, it provides a generalization of the Robinson-Schensted. So we're going to define some numbers associated to a poset. So we have K-Sperner families. We can also define dual K-Sperner families. To be subposets of P that doesn't contain anti-chains of length more than K. So, and as I said before, you can loosely think of K-Sperner families as unions of K anti-chains. and dual k-spinor families as unions of k chains. And then, okay, any questions? Okay, so I'm going to define some number let P be a poset. And define C of I to be the maximal size of a let me write CK of a dual k-spinor family. So you look at all the k-spinor families of this poset, and then you calculate the maximal size. In other ways, you're allowed to take k subchains of the poset and then union them and then calculate the total number of elements, and then CK will be the largest possible number you get from this process. And then meanwhile, we're going to define AK to be the maximal size of a k-spinor family. No. And here you're taking unions of k anti-chains and put them together and then calculate the maximal number of elements you can get. Okay. And then further, we're going to define lambda I to be Ci minus Ci minus 1. So you take differences of the Ci's, and then meanwhile we define a mu I to be a I minus a I minus 1. So so Greene-Kleitman proved some theorems about these numbers. Like there are two papers. The first paper is by Greene and Kleitman, a separate paper by Curtis Greene himself. And so I'm sort of putting all those results together. Theorem 1, I guess. Lambda 1 is greater than or equal to lambda 2. So the numbers lambda I that we get are monotone decreasing, weakly decreasing. And similarly, the numbers we get from the differences of the AIs are also monotone weakly decreasing. It is highly non-trivial, and the proof is also not very easy. So, but because they're decreasing, then we can think of these sequences of lambdas and mu's as two partitions. And so lambda I will be the number of boxes in the first row, number 2 will be the number of boxes in the second row, and so on and so forth. And so the second theorem that they proved is that these two partitions are, so if we let lambda be the partition lambda 1, lambda 2, and mu be the partition of mu 1, mu 2, and so on and so forth, then these two partitions are dual to each other. So dual means that the conjugate, or that you flip the Young diagram across the diagonal. So for example, the dual of this is that. And that's pretty amazing. Like somewhat you swap chains to anti-chains and then you kind of conjugate. So that's pretty nice. And so I'm going to give an example. Any questions so far about the definitions? So let's just take some poset. So the arrows are pointing down. He is this guy. And let's calculate the numbers, the C numbers. First of all, C0 is 0 because if you take if you take 0 chains, you can cover nothing. And then C1 is going to be the maximal size of a chain in the poset. And so this is probably the largest chain, the longest chain. And so C1 is going to be 4. And C2 is the maximal number of elements you can get using 2 chains. And you can already cover everything. You can already get 6 because this is the first chain that you can use. And this is the second chain that you can use. And so C2 equals to 6. And then if you keep going on, like you already covered everything. So you're not able to get, that's the maximal number you can get. So C3 equals to 6, C4 equals to 6, and so on and so forth. Okay. And if you take the differences, then you get lambda 1 equals to 4, which is C1 minus C0. Lambda 2 equals to 2, which is C2 minus C1. And then lambda 3 equals to 0, lambda 4 equals to 0, and so on and so forth. So you get a decreasing sequence 4, 2, and then infinitely many zeros. And you can, ignore the zeros, of course. Okay, I hope this makes sense. And let's calculate the A numbers. So A0 again is 0. A1 is the maximal size of an anti-chain. And then so here, for example, this is an anti-chain. This is an anti-chain, and this is an anti-chain, but you're not able to do any better than that. So the largest size of an anti-chain is 2. A2 will be the maximum number you can cover using 2 different anti-chains. And so here, this is my first anti-chain, and this is my second anti-chain, and I can cover 4 elements, but I'm not able to do any better than that. So A2 equals to 4. And if you want to use one more anti-chain to cover the poset, then you have to take this and then you can get 5. But you're not able to do any better than that. And then A4 equals to 6. You get everything. And then A5 equals to 6. Again, for the same reason, you get the same number if you want to use even more anti-chains. And if you calculate the difference is mu1 equals to 2, mu2 equals to 2, mu3 equals to 1, mu4 equals to 1, mu5 equals to 0, and then all the rest are 0. And if we draw the partitions out, the partition lambda is 4, 2, and the partition mu is 2, 2, 1, 1. And as promised, you get the dual partition. Okay. So, any questions?
I just want to know, is there a name for this theorem?
A name for this theorem?
Yeah, or like
The
a name
Greene-Kleitman theorem.
Okay, right.
Yeah. I mean, it's kind of a combination of several theorems, and there are several papers, but I think that this is usually how we call it nowadays. Okay, but there's more than that. So theorem 3, oh wait, actually, so let's just give this a name. Let me go back to here. So since these numbers are partitions, we are able to give it a name. We're gonna call lambda of P, we denote lambda of P of this partition to any poset. This is the Greene-Kleitman shape. Okay. And so if you take a poset P, is there a question in the? Oh, okay. If you start from a poset P and then you add an element to it and then get another poset P prime, let's say you attach another element on top of P, is obtained from P by adding an element on top. So for example, if P is this, then your P prime could be that. Okay. Similar statement will hold true if you add it on the bottom, but we're only going to need one side. Then the partition you get, then the Greene-Kleitman partition of P is going to be a subpartition of P prime, in the sense that the boxes of P are going to be contained inside the boxes of the Greene-Kleitman partition of P prime. Okay, and okay, so because of this theorem, then you're allowed to take sequences of posets and then get sequences of partitions, which will eventually become some kind of tableau. And so a corollary is that any linear extension of a poset and I should define things. So a linear extension of a poset is basically an order preserving numbering of the elements of a poset. And any linear extension of P corresponds to a tableau of shape lambda of P. It's not just a tableau, it's a standard Young tableau. And so here's how you do it. For example, if we take this poset here, let me just sort of do it by an example. And then a linear extension is a order preserving numbering. So here's something you can do. And then you can turn a linear extension into a sequence of subposets. So the first thing in the sequence is the empty guy, sorry, the one element guy labeled by 1. And then you take the subposet labeled by 1 and 2. And then you take the subposet labeled by 1, 2, and 3. The subposet labeled by 1, 2, 3, and 4. Then you take the subposet labeled by 1, 2, this guy is that. 1, 2, 3, 4, 5. And then you take the subposet labeled by everything. And so for every subposet you take, you calculate a Greene-Kleitman partition, and you're going to get a sequence of partitions. So let me just draw them out. The first is that, and this. 3, 2. So you get a nested sequence of partitions because of the previous theorem. They are contained in each other, and then you can turn this into a tableau by numbering the ith box using the number I. So here's a tableau: 1, 2, 3, 4, 5, 6. Okay, any questions? And you can use this to do RSK. Oh, sorry, to do RS, not RSK. And so here is how you're going to do it. So start from a permutation. Now W is something Sn. There's a poset that you can get from this permutation, which is going to be the inversion poset. The inversion poset of this permutation. So I'm going to define the inversion poset using an example. So basically, it's the poset such that, you know, if you get a covering relations from the inversions of the numbers. And so if my permutation is 2, 2, 5, 4, 1, 3, 6, then so I'm going to draw the rock diagram of this permutation. 2, 5, 4, 1, 3, 6. So you just label, well, you just put a dot on the second row for the first number, put another dot on the fifth row, and then so on and so forth. And then the poset is that, so, and I'm going to put arrows on these things. And then you have a single out kind of element. So it's not a connected poset. I see some questions in the chat. Are there better proofs of these things now than those in Brice-Fomin? I don't think so. I think Brice-Fomin is still the Bible of this. Okay, so so this is your inversion poset. Basically, every increasing subsequence of the poset is going to correspond to a chain, which means that I'm not doing it correctly. In what I am drawing, the decreasing subsequences correspond to chains. So I want to connect these things in the following way. Okay, so that's your inversion poset. So the increasing subsequences of your permutation are going to correspond to chains in the poset. For example, 2, 5, 6, you have 2, 5, 6, 2, 4, 6, 2, 4, 6, and 2, 3, 6, 2, 3, 6. And you also have 1, 3, 6. And those are the chains. Okay. And there exists two kinds of labelings two kinds of linear extension of the poset. One by column indexing and the other by row indexing. Oops. And here's what I mean. And then, so I'm going to add numbers. So the first number is that I'm going to label every element of the poset based on which row they're in. So this guy is numbered 1, 2, 3, 4, 5, 6. And the other linear extension is I'm going to number them based on which column they're in. So I get two linear extensions. I'm doing the first one in a wrong way. It's not order preserving anymore, it's order. This is the first column, second column, sorry, first row, second row, third row, fourth row, fifth row, and sixth row. The first column, second column, third column, fourth column, fifth column, and sixth column. So I have two linear extensions, and in the previous theorem says that for every linear extension, you can turn it into a standard Young tableau. So here I get standard Young tableau 1, here I get standard Young tableau 2. And then the theorem says there's another theorem. Which I believe is theorem 4, is going to be the following. So the SYTs you get are precisely P of W and Q of W. And bear with me, I always don't remember which one is P and which one is Q, but these two are the ones that you want. Okay. And so are there any questions?
Yeah, I mean, I don't know if you're gonna explain it, but how are the numbers assigned and how do you get the tableau?
The first is that you index them by column. The second one is that you index them by row. Sorry, the first one is row and the second one is column.
Okay.
So this dot is at the first row, so it's numbered by 1.
Right. And how do you read the tableau?
You turn this linear extension into a sequence of subposets. So here you I mean the orientation is wrong in this picture, is like kind of opposite, but if you have a linear extension, you can turn the poset into a sequence of subposets, where the ith poset is the subposet of numbers of elements numbered from 1 to I. And then you turn every those subposets into a sequence of partitions. And then because this is a nested sequence of partitions, every step you increase the number of boxes by 1, you can turn it into a standard Young tableau. Okay. Okay, so now I'm going to move on to to another way of doing RS, which is called the shadow line construction. It's also called the matrix ball construction by Fulton in his book. But I prefer the name shadow line because it was the original name. It's also kind of more romantic. And here is how you would do the shadow line construction. So you start from your permutation. And so for some purpose, I'm going to be using a different permutation here. Okay, so this will be our permutation. And imagine that you have there's a sun right here. It doesn't really look like one, but it's going to shed some lights on these things. And then, so it's going to create a bunch of cones on these dots. So these are the light cones that you see in the first step. And then you take the barrier or the boundary of these light cones, and that's going to be the shadow line. So that's a shadow line. Here's another shadow line. Here's another shadow line. Okay, and then we're going to remember the indexes of these shadow lines from the bottom and right boundary. And then, so these shadow lines are going to create new dots, which are going to be at the corners of these things. So now we turn to the next step. And we're going to draw some more shadow line on the new dots that we get from the previous step. And maybe I should erase, just for clarity, the previous things. And this is 2, this is 5, this is 2, and this is 6. And you get a new ball. And which is here. So the last step, you only have one shadow line, and you get 6 and 5. So Viennot proved that these numbers are the two tableaux that you get from the RS in the following way. So this guy gives you so 1, 3, 4 is going to be the first row of your P tableau. And similarly here, 1, 3, 4 is going to be the P tableau of the first row of your Q tableau. And then to the next step, you get the second row. Wait, did I say second row? Previously, well, sorry, these 1, 3, 4 are the first row of the Q tableau, and it's also the first row of the P tableau. And then 2, 6 is going to be the second row. Here, 2, 5 is going to be the second row. And then finally, 5 is going to be the third row. 6 is going to be the third row. So, okay, Viennot basically proved that this gives RS. Okay. So we have some shadow line that's happening. Okay, and what I'm trying to tell you today is some new observation, which might not be new, but that these shadow lines, they actually know the RS. Sorry, know the Greene-Kleitman duality. So you start from this permutation. And you have these collections of shadow lines. Ooh, wait. So there are some bumps happening right here. And if you sort of like collapse those bumps, you just get the rota diagram of this permutation. So it's kind of a deformation of the rota diagram. I mean, if you know what that means, if you don't know, that's okay. And so this is, let me call this the uncolored shadow line. So if you give it some sort of coloring, then it will tell you the information about the Greene-Kleitman partitions of your permutation or of the inversion poset. And then this will allow you to use the Greene-Kleitman theory to reprove Viennot's shadow line, or you can use the Viennot shadow line to reprove the Greene-Kleitman theory for the special case of permutation posets. And so let me copy this example to the next page. So before I talk about the next thing, are there any questions about this construction? Okay. Okay, so let me introduce a coloring of these shadow lines, which are kind of already implicit in the construction. So this first coloring, I will call the column coloring. Sorry, row coloring. It's going to be done in the following way. I'm going to color the shadow line in the first step of the algorithm by the first color, let's say red. So for all the shadow line that appear in the first step, they are going to be red. And for all the shadow line that appear in the second step, they're going to be blue. And then the third step is going to be green. So red means first step, blue means second step, yellow means third step, or the third row. Okay. And now with this coloring, you get the information about the Greene-Kleitman partition of this permutation poset. Basically, in the first step, these shadows that you get are all anti-chains of your poset. There are 3 shadows in the first step. It's telling you that the maximal length of a chain is 3, or the smallest number of anti-chains that you can use to cover the entire poset is 3. And by the way, this is Dilworth's theorem. And also, if you look at if you can place a partition at every box, at every vertex of this grid in the following way. So for example, I want to put a partition here. And then what I'm going to do is that I will look at this subdiagram. And then I see 2 red lines and 1 blue line. So I'm going to attach a partition on this vertex. Two, one. So 2 means there are 2 red shadow and 1 blue shadow. Okay, and then if you do this for all the vertices of this diagram, so, and then you will recover basically Fomin's growth diagram, which I will not talk about. But in terms of Greene-Kleitman theory, these are the Greene-Kleitman shape of the subposet. So you remember you have a permutation poset, the inversion poset of the permutation, and then you can pick any vertex on this grid and then look at this cone and then get the subposet. And then you can read off the number of red lines, the number of blue lines, and so on and so forth. And that's going to tell you the Greene-Kleitman invariant, the Greene-Kleitman partition of every subposet of this inversion poset. Okay, so the takeaway is that the shadow line knows the Greene-Kleitman partition. Or really, it knows the growth diagram. If you know what that means. So you get a way of coloring the shadow lines so that the first color corresponds to the first row and the second color corresponds to the second row and third color corresponds to the third row. And remember, the most amazing part of Greene-Kleitman theory is the duality, where you can like switch every chain to every anti-chain, and then you should get the same information because every time you're just conjugating everything. And then in terms of tableau theory, switching from chains to anti-chains is basically switching from rows to columns. So the question that you can ask is that, is there a way to get some sort of a coloring so that you know the first color corresponds to the first column, and the second color corresponds to the second column, and so on and so forth. So I'm gonna tell you how to do that. I'm gonna copy this diagram. And this is something that's really interesting. So turns out that in order to do that, you have to do the following construction. I'm going to create 2 copies of the shadow line. I'm going to imagine that my permutation is all of a sudden like bigger or something like that. And so and then you sort of do the same shadow line construction on this bigger permutation. Okay, just to need to make sure that I'm not making any mistakes. Oops. So, okay, let me try to just do this whole thing again. Okay, this is the first step of your shadow line construction. And you get some new balls here. And then I'm gonna do the second step. Like that. And then I'm going to do the third step. Wait, sorry. This goes here. And that. Wait, I'm kind of running out of time, right?
Yeah, but we can have like 5 more minutes if you want.
Sorry, I don't know why, but I'm confusing myself with this example. Okay, so that's the first step. And then this is the second step. Okay. At this point, I'm already done what should have happened in each of those two boxes. And then, so this should be the next shadow line from. Okay. Just use some color to help myself. Okay. This will be the shadow line that you get if you kind of take another copy of the permutation and sort of do it in this larger thing. And then I'm going to, now I can introduce the kind of coloring that I want to get the columns. And then it's sort of amazing that it's necessary to do this process. Okay, remember in the first step, there were 3 shadows. And then in the first step, I want the first shadow to be colored red and the second shadow to be colored blue. And the third shadow line to be colored orange. Okay, so previously these 3 shadows corresponds to the first row, and then the first row has 3 boxes, and each of the boxes belongs to different columns. So because of that, I want to color them using different colors. And then the rule is the follows: the other shadows are going to inherit the color of these 3 shadows, and so if they are adjacent, if they're attached to a shadow of color 1, then they're also going to be colored 1. If they're attached to shadows of different colors, then they're going to inherit the smallest color. And so I'm going to finish this. So this guy is connected to a red shadow, so it's going to be colored red. This guy also will be colored red. This guy also colored red. This guy also colored red. This guy also colored red. This guy is actually colored blue because even though it's colored, it's attached to an orange, but then here it's connected to a blue line, so it will inherit the smallest color. And this is blue and blue. This is not blue. Oh, wait. Okay, probably something's wrong in the example. There should be a. Okay, I mean something's wrong, but
If it helps, we can upload, you can figure this out later and we can just upload your talk notes.
No, I have this example here, but just like
Nice.
but okay, let me explain what is happening. So in the first step, there are colored differently. And then the other shadows are going to inherit the smallest color they are adjacent to. And then at the end, if you look at these guys, here, for example, you have 1, 2, 6, and 1, 2, 6 is in the first column. And then here you have 3 and 5. 3 and 5 is in the second column, and 4 is in the fourth column. So you can get the coloring associated to columns of your insertion tableau. So this part is correct, but something is wrong here. And so let me just conclude with a remark that why we have to do this. So this thing is recently discovered by in a joint work with Daoji Huang and myself. And the reason that we do this is that what's going on secretly inside this actual box is that you're using the translation symmetry of affine permutations. So affine permutations are permutations of integers that are periodic mod n, and then you can lift a finite permutation to an affine permutation by basically, repeated mod n. So every finite permutation is some kind of affine permutation. And then so really this is an infinite diagram. But it turns out that for finite permutations, only these two parts is enough. And then, so basically this coloring rule doesn't work if you just look at this finite shadow lines. And you somehow have to, lift it to affine and use the symmetry there to make the column coloring work. And so this is kind of amazing. Like usually affine stuff are more difficult, but it also has more symmetry. So something is easier in that case. So yeah, that's all I want to talk about. Like in some sense, this duality here that we are getting here is really kind of some kind of shadow of affine permutation. So that's kind of amazing. All right, so I'm going to end my talk here. Thank you all for your attention.
Thank you so much, Sylvester, for this beautiful talk. Does anyone have questions? I know we've had a good number through the talk. I can start us off. I've got, I mean, these diagrams feel very pipe dreamy. What's the connection to pipe dreams here?
The connection is that so there's no connection probably.
Okay.
Beyond that, bumpus pipe dreams are some kind of Rota diagram, the maximal bumpus pipe dream, and then these are all essentially some kind of Rota diagram. So yeah.
Nice. Okay, cool.
Yeah, I had a couple of questions. So you had this thing where you were making the tableau out of the posets and the column and row numbering. Can you see directly from that if you like reverse the permutation, you get the conjugate?
You can.
Okay. Is there like a nice?
So,
Yeah. So you can.
yes, if you reverse the permutation, then let's say you have W and W inverse, and then the chains in the inversion poset of W corresponds to the anti-chains of the inversion poset of W inverse.
Okay.
And then so the Greene-Kleitman theorem will tell you a lot of the
Mm.
symmetries of RSK, of RS.
Okay. Okay.
Yeah.
And when you're doing the shadow line construction for the basic Viennot construction, you make shadow lines and then you have new balls in some positions.
Mm-hmm.
Like the yellow circles and the green circles, are there interpretations for just like what that permutation is?
Oh, you're asking about this permutation?
Yeah.
Oh, those are not permutations anymore.
Right, but they're like not standardized permutations, but they're like,
Oh, you want to see them as like some kind of partial permutation.
yeah.
Okay, that's a good point. So, you can probably think of them as a partial permutation after you remove a increasing subsequence from your original permutation. But the thing is their positions are kind of off. So it's not a subpermutation of the original
Yeah.
permutation. But you can probably make sense of some operations. But I've never thought about it. That's a good question. Yeah.
Yeah. Like is the standardization means something?
I don't know. Yeah, standardization. Mhm.
So I have a question.
Mhm.
Very nice talk, first of all.
Thank you.
There's a lot of stuff here that I'd never really seen. So this Greene-Kleitman theory that takes you from these chains and anti-chains to basically the image of Robinson Schensted. So a standard Young tableau is basically a chain in Young's lattice. So
Right.
can you just say this all in terms of poset maps, like go from an arbitrary poset to a map in Young's lattice?
You mean, oh, I see.
Because you're mapping to a pair of chains in Young's lattice.
Right. There's probably if you replace the Young's lattice with some sort of, I'm not sure if it's a lattice anymore, but let's say it could be a lattice of like linear extensions of a poset. Then maybe you will be able to make sense.
No, well, I
Something
actually
like
really
that.
want to think of it in terms of Young's lattice. I don't know if the lattice part is important, but because then that gives you a way to map, I don't know, directly to the representation theory, I guess, is what I was thinking.
Yeah, I think like the reason that you can interpret RS using half of the Young's lattice is because it's a differential poset, and there's this up operator and down operator, which satisfied, the correct commutation relation. And I think the hope of generalizing this is not very much, because I remember there's a classification of differential posets, which basically is like when certain things can happen. There's, I think Vic and maybe one of his students many years ago sort of had some sort of classification of what can be a differential poset.
Okay.
And yeah, like so basically here these chains are just linear extension of the poset, and different chain will just be a different linear extension. And yeah, I don't know how to make more sense of this in terms of Young's lattice. Maybe other people will know. Yeah, sorry about that.
No, thank you. And the other quick question I had was when you wrote down GK, are you referring to like Fomin's growth diagrams? Is that?
I'm referring to Greene-Kleitman.
Okay. All right.
Where did I do
Said
that?
something about, I think, growth diagrams. Yeah,
Yeah,
growth
but
diagram.
yeah, oh, I see. So the fact that the shadow lines knows the Greene-Kleitman partition is because that you can use it to recover growth diagram.
I see. Okay.
So Viennot had a secret paper which does that.
A secret paper.
Yeah, yeah.
Okay.
He gave some lectures in India, and then like some of his lecture notes turned into a conference paper, and where he explains how to use shadow line construction to recover the growth diagram.
I see. Okay.
Yeah.
Thank you very much. It was a great talk. Thank
Great
you.
question.
Yeah, one question about the growth diagrams. Is there like a way to go from growth diagram to making a shadow line construction?
Yeah, that's what I was talking about. So I mean, I can tell you how to do that.
Or like in general, like there are growth diagrams for a shifted tableau, for example. Could you do like a shadow
You can
line
try.
type for shifted tableau?
You can try shifted tableau. I don't think it existed in the
Mhm.
literature, but that's something you
Okay.
can try. Yeah, maybe you can write a paper about it. I don't know. Like, yeah.
Yeah,
So if you want to translate shadow line to growth diagram, you just number the edges. If it's connected to a red, and you just number it by 1. If it's nothing, you number it 0, and then 2, and then so you get numberings on the edges, and then there are 4 different rows. You can have either all 0, or you can have 0, 0, 1, 1, or you can have I plus 1, I plus 1, or you can have I, and J, J, I, J different. And then so these rows on the edges will recover the shadow line construction. And this is basically the growth diagram. So
nice. Thank you.
yep.
Okay, now we could stop the recording and go to the underground questions.